we've got it down. All right, so what did we leave off talking about last time? Last time ended by talking about the analogy between classical mechanics and thermodynamics. You won't be tested on this at all. But that was the last thing that we mentioned, and we derived all of the different new thermodynamic identities for the enthalpy, the Helmholtz free energy, and the Gibbs free energy. Okay, so now what we're going to do is we're going to discuss the section titled Free Energy as a Force Toward Equilibrium. And basically what we're going to do is we're going to kind of like transform how we think of the second law into a way of thinking about it in terms of these new thermodynamic quantities. So basically something that all the stuff we've started talking about has in common is that we're not really considering like necessarily an isolated system. So we know that for an isolated system, that what does the entropy have to do? What does it have to do? Or, yeah, never forget that. Either increases or stays the same. Okay, but what if we're not talking about something that is isolated? So the way we should think about this is we're going to have some system sitting in some environment, and we're just going to consider the system in and of itself, but it can actually exchange things with the environment that we're going to completely neglect and not track whatsoever. Whoops, don't screen share. Keep the chat open. Okay, so we had discussed the notion of theoretical reservoirs before. So what we're going to do is we're going to assume that for all the things that we're talking about, that our environment that our system is sitting in, that it acts as a reservoir. So it's so big that it can exchange heat with the system, and its temperature does not change whatsoever. So that's our assumption. We don't need to assume that. Can absorb and release heat without delta T changing. Okay, so that's just the definition of a reservoir. So what we're going to do now is we're going to take the total entropy of our entire system, or technically our system plus our environment. So the total entropy of this whole thing right here, we shouldn't probably call it our system because we're calling this our system, but we'll call it the total entropy. It's going to be the entropy of the system plus the entropy of the reservoir. Okay, so it's just taking the differential of this, straightforward. And we can use the thermodynamic identity. Which says that ds is equal to 1 over t du plus p over t dv. I left off the dv in my notes. Mu over t vn. So if we assume that energy is the only thing that flows between the reservoir and the system, then we can write ds total is equal to ds plus, eraser, dsr, the reservoir, which in this case is going to be just ds plus 1 over t, temperature of the reservoir, times the change in the energy of the reservoir. So we were able to rewrite this as this just because the only thing that's flowing is the energy. So nothing else is changing. So it is just this term because dv and dn are just 0 in this case. And I need to pause a quick second because I've got a cat who's trying to claw out of my room. So give me just one quick moment. And we're back. Okay. So if we are in equilibrium, then what that means is that the temperature of the reservoir is equal to T, where the temperature T is just the system. Relatable. George, do you also have a cat who demands to either be in or out of your room whenever the door is closed? I sure do. Okay, so in equilibrium, we have that the two temperatures are equal. And we're always going to have that since these two things are coupled to each other, when energy goes out of one, energy goes into the other, that the change in energy of the reservoir is going to be equal to minus the change in energy of the system, right? So we can rewrite this further. So we can say that ds total is equal to ds, the change in entropy of the system, minus 1 over T du, because now all we're doing is we're just writing this at equilibrium. And so we're using the fact that we just wrote right here, putting it into ds total. Thus, we have the following. If we pull out a 1 over T of the whole thing, we can write this as du minus T ds. But what is this quantity right here? Anybody? What's du minus T ds? df, exactly. So this is 1 over T df. So we have that at this point, we can basically restate the second law, which is that the entropy either increases or stays the same, as the same thing as maximizing the system's decrease in Helmholtz free energy. And so we assumed that energy is the only thing that flows. And if you also assume the second law holds, then this has to be the case, right? So if ds is supposed to increase or stay the same, this has to be a negative quantity, or it has to be 0. So that's that. So basically, what we're going to do is we're going to forget about the reservoir from here on and simply remember that we want to decrease this quantity. We want it to be the smallest we can, the most negative. So that it'll make df as negative as possible. Okay, again, this is just assuming that only energy flows. Okay. So now we're going to let another thing flow or change. What might that be? It'll be the volume. So we're going to let the system volume change, but we're going to keep it at constant pressure. Yeah, Jacob, go ahead. Mm-hmm. Well, so think about it in the exact same way that you would think of a system tending toward maximizing entropy. So the statement of maximizing entropy, remember, was a statement about the number of microstates corresponding to a system. So all we're saying here now is that that same statement, at least if we're assuming that energy can only flow between a system and its environment, would correspond to the making this df as negative as possible. So did that answer your question at all? Maybe you can say it one more time. Well, okay, so what we're talking about here is not like non-equilibrium thermodynamics. We're talking about equilibrium thermo, and specifically, like, I mean, this whole thing right here, at equilibrium, if like the two start off in different states, the whole entropy has to increase. We're never going to talk about the case where it could possibly decrease for a period of time and then increase further, right? We don't worry ourselves with how it gets from where it starts to where it ends. We just know that at equilibrium, it's going to have to either increase or stay the same. Is that elucidating at all? Because I mean, I think what you're getting at is you're wondering like how you go from effectively like a smaller entropy to a bigger entropy, and that's something that we're not discussing whatsoever. We only talk about the equilibrium states, so we only talk about the ends of this process. It's the same thing here. Okay, but that is a good question. And it's something that you'll, if you take like graduate level thermodynamics, you'll definitely discuss and learn how to calculate stuff like that quantitatively with much more rigor than we're doing right now. All right, so yeah, previously we let the energy change. Now we're going to let the system volume change. But what was I going to say? I should say keep pressure. So keep both the system and the reservoir at constant pressure. So in this case, we're only exchanging volume. Then we can write ds total, the total change in entropy, as the change in entropy of the system. Again, 1 over T du, just like we did previously. That's the same expression that we had here before, after we used this fact right here. And also this time, we'll also have this term right here. Okay. So if we rewrite this a little bit, we can write that as 1 over T du minus T ds plus P dV. And that, does anybody know what this quantity is right here? Anyone at all? Du minus TDS. So yeah, it's basically G. It's dG, right? So it's minus 1 over T dG. G would, yeah, that's exactly right. So now in the situation where we're also allowing the system volume to change, in addition to the system's energy, now the second law can be stated as making this change in Gibbs free energy as negative as possible. And maybe this is asking some questions that were being asked. Maybe this is answering some questions that were being asked on Monday when I was saying stuff like, oh, a system will like tend to want to go toward like one of these negative changes for the Gibbs free energy. So what we've just showed is that the second law of thermodynamics can be restated in the specific system as just being making this change in Gibbs free energy as negative as possible. So let's just recap all of this. So we've got 3 different points we want to make. So if we had constant U and V, then in that case, the entropy is the thing that tends to increase. If we have constant temperature and volume, then F tends to decrease. This is just summarizing what we've said. So if we have constant temperature and pressure, then G is the thing that tends to decrease. And all of these statements right here, they all assume that there's no particles being exchanged. Okay. So let's intuitively understand these relationships a little bit. So we have our definition for f. It's defined as u minus ts. So if f is decreasing, and that means that s tends to increase. Sorry, that was an incorrect statement. Yeah, so if f is decreasing, means that s tends to increase, then we should think of u tending to decrease, right, to make this overall negative. But why, if we're talking about the system in and of itself, why would the system energy, this u, tend to decrease? Does anybody have any thoughts about that? So if the total entropy is increasing, why would we think of this u as decreasing intuitively? Where is this energy going? So it starts in the system. Where is it going if f is decreasing? Anybody? Or does that not make sense? Yeah, the environment. Exactly. So yeah, so if the entropy is increasing, this energy is just going to the environment. And then a similar statement. So G is defined as U plus PV minus TS. So now if we have decreasing G, and that means that S tends to increase, while U and V tend to decrease, right? So in this case, why is V tending to decrease? Well, it's tending to decrease because it's giving up volume to the environment. So that's just how you want to think of these two things if these things are decreasing. All right, so hopefully that wasn't too confusing. Sometimes it can get a little confusing when you start just talking about the system and completely neglecting the environment, but hopefully you can get that pretty clear in your head. So now we're going to talk about a kind of, yeah, Safe, what's your question? Mm-hmm. So I'm just holding constant the things that were set up here. Correct. That's what we assumed when we basically said this statement right here. Yeah. But so if we're only looking at the system, and not looking at the environment, then we want to talk about this rather than S, right? Because the total entropy of the system and the environment increases overall. But if we're only focusing on the system itself and neglecting the environment, then we want to talk about this Helmholtz free energy and this Gibbs free energy. Does that make sense? The entropy of the system should be increasing as well. Yeah. But the point is that we don't necessarily want to even think about the entropy of the system, because in those specific cases, these are the relevant quantities to those, because you're allowing it to exchange temperature, or not temperature, heat with the environment, or heat and volume with the environment. So you're not tracking those quantities. So now these are the relevant things to talk about rather than entropy. But it would be true that entropy is still increasing. Entropy better increase overall if you're talking about any thermodynamic system. Okay. Yeah. So, I mean, the reason it was negative in the things that we've calculated so far is because we're talking about reactions going in a certain direction, in the direction that they prefer to go. So like, for example, if you took like the previous lecture where we talked about like taking like a half of an oxygen O2 and hydrogen H2, those two things they want to combine into H2O. So that's why in that case, G tended to decrease. It was negative, right? So if you were now talking about the opposite thing, if you're talking about wanting to like take H2O and break it up into those two things, now G is going to be positive because that's not something that wants to happen. You're going to have to put in that energy to make it happen. Does that make sense? Okay, cool. That's a good question. Okay, so now we're going to introduce some new concepts. So we're going to talk about extensive and intensive quantities for thermodynamic systems. And honestly, when I learned thermodynamics, like this was the first thing talked about, so it's a little odd that it's laid in, but I guess it works. So I guess at this point, you've got like a big old just like list of thermodynamic quantities that you need to remember the relationships between. So thinking about them in terms of these two different properties is going to be a kind of way to organize them effectively. So what are they? Well, extensive just means that it's some quantity that is proportional to the system itself. So if you take a system and you like double it, then these quantities would also double. Okay. So these are things like energy. Take a system, you double it, you got twice the number of systems that you had before, now you've got double the energy, obviously. Same thing for volume. If you take like a block as a system and then you put in another block, well, now there are two blocks, so it's double the volume. And then the same thing for entropy, because entropy is additive as well. So that's extensive. Intensive quantities, you could probably guess, are just things that are not extensive, so they're not proportional to the system. So these are things like, let's say, pressure and temperature. So if you double a system, the pressure doesn't necessarily have to increase or decrease, it just stays the same if you're just taking two systems rather than one system. And then same thing for the temperature, that doesn't actually need to change if you're just doubling a system. So if we wrote out a full list for each of these, it would be, we'll make some little lists right here. So all of the extensive quantities are going to be volume, number of particles, entropy, the energy of the system, the enthalpy, the Helmholtz free energy, and the Gibbs free energy, and also mass. Okay, intensive quantities that we've discussed so far are temperature, pressure, chemical potential, and the density, rho, mass over volume. Okay, so these are the definitions of these two different types of properties for different thermodynamic quantities. From these, we can develop some algebraic rules for working with them. So here I'll just use E's and T's to talk about extensive versus, or sorry, E's and I's to talk about extensive and intensive. So here are the rules. If you have an extensive quantity and you multiply it by an intensive quantity, that gives you an extensive quantity. Hopefully that makes sense why that's the case, because if you just take something that doesn't scale with the system, multiply it by something that does, then that thing should still scale by the system because this didn't change that quantity by anything with respect to scaling of the system. So E times I is equal to E. An extensive quantity over an extensive quantity, if you divide them, what do we think that should give? Any thoughts about that? So if they both scale with respect to the environment, then if you take their ratio, would you expect that to scale with respect to the environment or not? Yep, that's right, Alex. So this would be an intensive quantity. Samesies. Yep, Jacob, you are also right. Okay. we could also do an extensive quantity plus an extensive quantity. That would give us an extensive quantity. We could take an intensive quantity plus an intensive quantity. That would give us an intensive quantity. We could also take like an extensive quantity times an extensive quantity, but what the heck is this going to be? It's going to be like doubly extensive. So if you ever see anything like this showing up in your calculations, you've done something wrong. And so this is actually a good technique, kind of akin to doing dimensional analysis, that you can use throughout your calculations, because at the end of the day, if what you're talking about are things that you can observe, it's either going to have to be an extensive quantity or an intensive quantity. There's no such thing that scales like doubly extensive if you double the system. It doesn't scale by 4 if you do that. No such thing. So don't do that. Question? Yes, Jacob. Yeah, so it'd mean like, yeah, so it'd be, oh, let's see, like taking the volume times the number of particles. What is that? It's nothing. The only way these two things show up in relationship to each other, at least like in one way that we've seen, is like through the ideal gas law, right? And so in that case, the ideal gas law obeys something that looks like PV equals NKT. So that's all well and good because we've got an extensive quantity times, or sorry, an intensive quantity times an extensive quantity. And then N is intensive and N is extensive and T is intensive. So you would never see something where you calculate like some quantity, let's just call it X equals N times V, is all I'm saying, because like this X would not correspond to anything that you can actually measure. Like, yeah. I don't know if that makes a whole lot of sense, but yeah, you say you got it better, so I guess it worked. Okay, so yeah, just basically if you ever see a doubly extensive thing like this, you've done something wrong. Go back and check your work. But it is a good tool to know this in order to actually check your work without going into too much detail. Is there anything else we need to say? We should also probably say that obviously, maybe not obviously, you should never see anything where you're adding an extensive and an intensive, because then whatever appears here on the right-hand side is also just like some nonsense combination. It'd be like taking the volume plus the temperature with some scaling factor in there. That's also something that's never going to show up. Let's see. Another thing that you will see is, so for example, one calculation we've done over and over again is calculating the multiplicity for a specific macro state, right? And that looks something like e to the s over k, because s is just equal to k log omega, right? So the multiplicity is the exponential, it's the exponentiated extensive quantity. So in that case, what happens is, well, we know that omega total is equal to omega times omega if we've got two systems and we double it like that. So in that case, this would look like 2s over k. So this is something you will see, potentially. Okie doke. So now I've got a quick question. So let's try to answer this. Is heat capacity, big C, not little c, is it extensive or is it intensive? Does anybody have any thoughts about this? So if you double a system, intensive, but I want to hear some explanations here. So open up your mics. Tell me why you think this. Jacob says he can explain. Q over delta T. So little c is big C over M, but we're talking about this right now. That's okay. Does anybody else have something? Mm-hmm. Mm-hmm. Okay, so well, let's break this down. So what does this Q here represent? It's the amount of heat you have to add to change the system by some degree that you specify, right? So it's the amount of heat that you have to add for a specific object, right? So if we take that object and now we double it, how much heat do you have to bring it up by the same amount of temperature? Anybody? Anybody at all? Oh, chat. Double. Yeah, exactly. So because this heat right here is the heat for a specific system in order to change it by some temperature, if you take the system and you double it, well, now you've got to add double the heat. The heat added to change that doesn't scale on any other way other than with the system. So this one's a little tricky because I don't think we had actually said that like Q specifically, like heat, is an extensive quantity because it depends on what kind of heat you're talking about here. But here, the heat that you need to add is specific to the system. So if you double the system, you double the amount of heat you have to add. So this is extensive. All right, so check mark there. So maybe we got a little bit ahead of ourselves. What about specific heat capacity? So C is defined as big C over the mass. How can we use our algebra? We've got an extensive quantity right here. And what is mass? Is that extensive or intensive? Will it double with the system or will it not change if you double the system? Yeah, I think Grant's got it. So overall, this is an intensive quantity because these are both extensive, right? So this is extensive. This is extensive because if you double the system, the mass doubles, obviously. And if we just said before, if you double the system, the heat capacity doubles. So overall, this had better be intensive because scaling this entire thing, if you scale a system, if you're taking a ratio of the two things that scale with the system, well, then that scaling just cancels out altogether. And so you're just left with an intensive quantity. Everybody cool with that? Would it be fair to say that you can look up intensive quantities on a table, but not extensive quantities? What do you mean? What do you mean look them up on a table? I mean, oh yeah, no, absolutely, because this is specific to the system you're talking about. So like this is specified for a certain type of matter. So it's true that you could look this up in a table, but I'm not sure I'd extrapolate out to all intensive quantities you can look up on a table because like what did we say? Like the temperature of a system, that's not like what kind of table are you talking about in that case? But I mean, I like how you're thinking, but it is true that you could look up the specific heat in a table. But yeah, I wouldn't extrapolate that out to all intensive quantities. Okie doke. So that is our new terminology that we've picked up. We're a little bit over, but we're going to keep going, like I said. We're going to disregard the time that I had initially said, because we've got content to cover. So, what are we going to talk about now? Well, we're going to talk about the Gibbs free energy again, and its relation to chemical potential. All right. So first of all, let's recall the thermodynamic identity for the Gibbs free energy. Does anybody remember it off the top of their head? It's probably kind of hard to write in chat, so I don't know if I'd recommend doing that, but I'll just write it. So it's D on G, the change in the Gibbs free energy, is equal to minus the entropy times the change in change in temperature, plus the volume times the change in the pressure, plus the chemical potential times the change in the number of particles. Okay, so from this relationship right here, how could we write the chemical potential? Thoughts? Somebody. I wish I could just like light up somebody's screen. Is there any way to do that? Just like completely call people out. Oh, spotlight video. Maybe I can actually do that. That doesn't seem fair though. So I think you're on the right track, but so we want to isolate mu. So we don't want all this other junk hanging around, basically. So if we just want to isolate mu without this stuff right here, maybe this is not really a great question because you could write it with all the other stuff. But one way to neatly write it, just in terms of changing one other quantity rather than all the other quantities, that's what I should have said. Yeah, is having T and P be the same. That's right. Yeah, that was just a poorly worded question, so that's my bad. So if we want to write it in terms of just the change of one other quantity, then you could write it as del G, del N, and we're holding T and P constant. So we can think about this now as we can hold T and P constant. Then we add one particle, it changes G by an energy. Remember we said that chemical potential has units of energy, mu. Okay, so adding a particle just changes the Gibbs free energy by mu. So we can integrate this up. Integrate. And we can get that G is equal to N times mu, specifically. And so in this case, the integration took place and we just set that the lower bounds for G and N are set to 0. So we're integrating from 0 for N and G. And this is also specifically for one type of particle. If we had multiple types of particle, then this would look something like a sum over I, N sub I, mu sub I, where these are just the numbers of particles with some specific chemical potential. Okay, now let's do something similar. So we could ask, couldn't we do the same thing for F? Well, what's the thermodynamic identity for F? It's dF equals minus S dt minus P dV plus mu dN. So if we wanted to relate the chemical potential to the change in just one other quantity here, and specifically the Helmholtz free energy, how could we do that? I want to try the spotlight video feature, but I know whoever I try it on is going to hate me. Let's go with, well, no, I'm not going to do it. I'm not that mean. All right, I'll just answer it. So you're probably all thinking of this and you just don't want to say it. So just hold having the rest change in quantities unchanged. Yeah, exactly. So, I mean, we're just, hold T and V constant, and then you can solve for mu in terms of the derivative on F. So you might say, oh, so it's the same as before. So what we had just shown before in the previous page, that mu can be related to the derivative of g on n, and thus we can interpret adding a single particle as changing mu by an energy, or changing g by an energy mu. So you might say that, oh, it's just the same. It is not the same. Why isn't it the same? Do you have any thoughts about that? Why can't we just interpret this in the same way? Why can't we just say that mu is equal to, or like the same way as this? So why can't we just say that f is equal to n times mu? I think George has it. Yeah. So the volume changes, right? So we're holding v constant instead of p. Yes, exactly. You're all paying very good attention. Good. So yeah, in this case, we're holding the volume constant. And if you add a particle to the system while you hold the volume constant, well, then each time you do that, this is going to change, right? Because you're effectively putting a particle into something which is now more dense, and the way you think about chemical potential is basically just like how hard it is to like insert another particle into the system. So if you have a higher density of these particles, then it's going to be harder to put in. So you can't just interpret this in the same way as the previous one, because previously we didn't hold the volume constant, we just held the pressure constant. So do not just think that you can write F is equal to N times mu. Don't do that. Okay, so let's take the good relationship. So let's take G is equal to N times mu. Thus, mu is equal to G over N. And we can take the derivative with respect to the pressure if we want to. That will just be 1 over N del G del P. But here, we're just going to have that del G with respect to only changing pressure. It's just the volume. So this is just V over N, just using the thermodynamic identity there. And if we then change this into KT over P, so if it's an ideal gas, then we can relate V and N to just the quantities that appear in the ideal gas law, and so we can rewrite this as KT over P. So basically, we have an ideal gas, then this is the case. And so at this point, we could integrate mu, integrate d mu, just move the dp over to the other side. Integrate kt all over p dp. And if we integrated this from mu at some temperature T to, and P, we'll call this like atmospheric pressure, the P with the circle, to some other pressure at the same temperature, P, same thing over here, then we could integrate this and we could find the relationship for how mu changes as you change the temperature or the pressure. And we're not really going to use this at all, but this is something that we just wanted to show that we can do if we want to find the chemical potential at a different pressure for an ideal gas. This is how you could do it. Okay, so I think that's actually probably enough material. Well, no, we're going to keep going just a little bit further. Okay, so that's that. Now, yeah, question. Go ahead. Mm-hmm. Yeah, so we held the pressure constant to find this differential relationship right here. So this is at a specific pressure. We integrated it, and we just said that we can write this relationship now. just that g is equal to n times mu, regardless of that assumption at this point. And so now we're just saying if you know mu at a specific pressure, you want to find it at a different pressure now. Not that the pressure is changing over a process, but that you want to find what mu is at a different pressure, that you could just do this integral like this. So basically we shedded the assumption of this when we integrated and then used that formula. Yeah, absolutely. Well, I mean, here we're not really talking about like a specific process, right? We're just talking about like these differential relationships between the two. And so you would only use this expression to find mu at one constant pressure and relate it to a different mu at a different constant pressure. You're not going to use this like when the pressure is changing over a process necessarily. Okay. Cool. All right, so now we're getting into the end of chapter 5, which is dealing with the very exciting topic of phase transformations, and specifically of pure substances. We will not be talking about phase transformations for mixtures. We're going to leave that off entirely, just because basically everything follows if you understand pure substances. So what is a phase transformation? Does anybody have any examples? There's the typical ones. Ice melting, yeah, ice to water. So what is it that's happening at a phase transformation? How would you describe that to somebody who doesn't know what ice or water are? Scary molecular changes, breaking bonds. Yeah. It doesn't have to be necessarily breaking bonds though, right? Like things can come together microscopically. Yeah, so I mean you all want to think of it as only the one directional phase change where you're breaking into molecular forces or something, right? But basically what it is, it's whenever you have something that goes from what we call phase 1 to some other phase 2, and these two are just supposed to be qualitatively different based on how they behave, right? So, I mean, liquid is one phase of matter, behaves differently than some other gas. And so just going between the two is what we call a phase transformation. So that is a phase transformation, qualitatively speaking anyway. It can also be called a discontinuous change in the properties of a substance as the environment changes infinitesimally. That's the more proper definition. So we're going to look at specifically everybody's favorite phase transformation diagram, which is that for water. So if we try to recreate this, so usually we've got pressure on one axis and the temperature on the other. I'm just recreating the diagram that is in the book. So this is 0.66, and these are in units of bars. I think up here is like 2.2, or not 2.2, 221. So water has this really interesting phase diagram, right? Got 0.01 Kelvin here. And we've got, let's say, 374 Kelvin down there. So water has got something that looks like this. So that is the triple point. It's a critical point. And this is almost straight, but it tilts to the left just a little bit, which is a key feature of water. It doesn't look exactly like this. It's basically just a straight line that goes over that way. So in this part of the diagram right here, you have the phase that we call liquid water, right? Liquid H2O, water. Over here, you have the phase which we call ice, which is just solid water. And over in this region, you have steam, which is just the gaseous form of water. And so this point right here is basically a point where all of these three phases can coexist. So you can think of all of these lines on this phase diagram as being the lines where you can have a mixture of the two different phases existing in equilibrium, right? So like at any point along here, you can have a system where there are equal parts which are equally likely to be either water or steam. It's kind of weird to think about, but it's true. And even weirder is that with water, you have this point right here, where you can have all three of these states coexisting in the exact same system at equilibrium. So this is called triple point. This point right here has a different name. It's called the critical point. Critical point. And so what happens here is that as you increase the temperature and the pressure, at some point, the distinction between what is liquid H2O and what is gaseous H2O becomes completely indistinguishable. You can't tell the two apart. And so this point right here just denotes where that actually occurs. So everything over here is just whatever you want to call it, and people typically just call it a liquid. But it's a point where the two different phases start to kind of blend together. So note, yeah, is it supposed to be Celsius? Is it? Yes. This should be Celsius. Yeah, because we're talking about freezing right here. Yeah, that should be at like 0 degrees Celsius, not 0 degrees Kelvin. Oh, that's a good catch. That was just a dumb mistake on my part. So obviously, you can't have minus 273 degrees Kelvin. That's a non-existent thing, unless we're talking about paramagnets, right? Then we can have negative temperatures. But here we're explicitly not talking about systems that are finite, like the paramagnet. So yeah, can't imagine what water looks like past the critical point. Yeah. Yeah, I can't honestly imagine exactly what it looks like either. This is a temperature and pressure that I would never want to exist with my body at, right? I don't want to be anywhere around here and still be alive. I'm dead, whatever. Throw me over there, I don't care. So one thing I want to mention is that this diagram is all talking about, at every single point of this diagram, you're always talking about an equilibrium, equilibrium states. And so what this diagram doesn't actually depict are these so-called metastable states. So the boiling point is the critical temperature of a substance. Wait, no. Boiling is at like, what, 100 degrees Celsius, right? So boiling somewhere over here. So the thing that I was just trying to mention was just that this doesn't depict these so-called metastable states, which we're not really going to discuss a whole lot, but metastable states are just effectively, they're semi-stable points of equilibrium, but they're not the ultimate equilibrium that a system can reach. And some examples of this are things like supercooled water. So if you've ever seen, what's the fun one that people always show? It's like where you take a water bottle and you cool it really, you don't open it or anything, and then you cool it, and then you open it or something, or you like hit it on a desk or something, and that just like automatically freezes the water. So that's an example of a metastable state, because basically in order to actually change from the liquid to the solid, you need a so-called seed structure. And because bottled water typically has not very many minerals, it can come into this supercooled form. And so this process is called nucleation, and that's not something we're really going to discuss a whole lot. Isn't the critical point the point where liquid and gas phases kind of meld together? Yeah, that's what the critical point is saying right here. It's the point at which the liquid phase, which is water, and the gaseous phase, steam, they meld together. They're indistinguishable at that point. Do we have functions and models that predict these plots? We do have a deeper understanding of exactly how you can arrive at this kind of stuff. And actually, one of the things we're going to talk about toward the end of this chapter is the Clausius-Clapeyron equation, which can tell you how to actually calculate the slopes of these phase intersections. But yeah, I mean, understanding like phase diagrams and whatnot is a really really big field of research, and stuff like this comes up not even just in like typical matter, but it can come up in like quantum field theory, and all kinds of other interesting stuff in condensed matter. So yeah, phase transformations are a big deal. One other definition that I wanted to throw out is that of vapor pressure. So vapor pressure is basically just the pressure where gas and solid can coexist, and it just gets a special name because it's that thing. And so the vapor pressure would correspond to the pressure along this line right here, where the solid and the gas can coexist. And specifically, the vapor pressure is like the pressure at any point along there, right? So that's just what we mean. All right, well, that is basically all I want to talk about right now. When we come back, we'll discuss a little bit further. Yeah, like sublimation processes, right? Because you can go straight from a solid to a gaseous state if you just go through this part right here, right? So if you're at like really low pressures or something, or if you're at really hot temperatures or whatever, yeah, sublimation is another thing that can happen. All right, so yeah, we'll come back. We'll talk about this some more. I don't want to go too much further over today. But are there any questions before we leave? No? Don't see any. Oh, there was one announcement that I think I wanted to make at the beginning of class, which was that I posted most of the grades for homework 2. Those are up, so if you see any issues with that, make sure to contact me right away so we can get that fixed. And homework 3 and 4 will be graded as soon as possible. And I guess since it's Wednesday, I can now post the solutions for homework 3 and 4, so I'll do that today. So look forward to seeing homework solutions online, and yeah. And we'll also figure out a definite time for the final exam. So make sure to fill out the doodle poll. Okay, well, if there are no other questions, you are free to leave and go about the rest of your day as you choose. Thank you for being here. See ya. Yeah. Yeah. Can you say that again? I'm not sure I totally understood.